Alright, so here's the second half of 5.2. Why is that light blinking? Hope that's not a bad thing. Anyway, so 5.2 continued in the first half video. We looked at the notes, right? For 5.2, we looked at the substitution method, and that was one of the more reliable algebraic methods. You know, no matter what the answer is supposed to be, these algebraic equation methods will flush them out, no matter how ugly or nice or whatever. So there's not just one nice algebraic method, there's two. And the other one is traditionally in textbooks and most teachers and whatnot call the elimination method. I like to make things complicated. No, not really, but I like to call this the addition method. I don't know, I like that name better. Because I like to stick with the addition and not the subtraction, but I'm getting ahead of myself. So here we go. Firstly, it's worth pointing out that you're going to run into some systems, and you know what, this one's not even a good example of what I'm about to say, but you're going to run into some systems that you look at it and you go, man, I can probably use the substitution method, but it's going to be a rough going, you know, like it's going to be real tough finding a variable at the beginning that I can like easily, cleanly solve for, you know, and get it ready for the substitution method. You're absolutely going to run into systems like that. This is actually not a good example of that, because if you actually wanted to do the substitution method on this system, it wouldn't be that tough at all to solve for that x. But real quick, let me just kind of don't write this down. But what if it was like 3x minus 7y equals 2, and the other system was like negative 4x plus y. I'm an idiot. Plus, took my eye off the prize for a second. I lost track. Negative 4x plus 5y equals negative 1. You know, a system like this, man, no thank you. I don't want to solve for that x. I don't want to solve for that y. I don't want to solve for that x. No. So, So anyway, it's good to have another method, right? It's good to have another method. And the idea behind this elimination method is to, well, quite frankly, eliminate one of the variables by adding the two equations together. Eliminate one of the variables by adding the equations together. Now, what could go here, which I've sort of, scribbled out, by adding or subtracting, So think about it. If I wanted you to add two equations together, how would you even do that, first of all? But yeah, if you're totally new to this concept, that's what we're going to want to do, is actually add two equations together. And yeah, you can actually also subtract equations together, but I like to keep things a little simple, just adding, which is why I feel more than free to refer to this method as the addition method. Not to mention that subtracting is technically adding anyway. But yeah, so here we go. What is this method going to be really all about? And step 0. If we are going to actually add an equation to another equation, step 0, we need to make sure everything is lined up. What does that mean? That means that the like terms, like the x's, need to be lined up, because when we add the equations together, we're only going to be able to add like terms to other like terms, right? So the x's need to be lined up like this. The y terms need to be lined up. The equal signs need to be lined up. And these number constants, also, we're going to want them lined up. So everything that can add together is going to be lined up. And step 1 is make sure there's a pair of opposites, okay, contained in the like terms. Again, I'm going to write down something that you do not need to write down. In fact, you probably shouldn't. Imagine I had another system. I want to write down a different system for comparison purposes. Imagine, again, don't write this down. Imagine you had one system was like 2x minus 3y equals 8. And the other system was like minus 5x plus 9y equals negative 5, you know? If you were to go ahead and add these two equations together, just watch, don't write, what would you get? Adding the x's together would get you negative 3x. This would get you plus 6y. Bring down the equal sign. Then 8 plus a negative 5 is positive 3. Where does that actually get you? I'll tell you where. Nowhere. This got me nowhere. Okay, so now I have a third equation of negative 3x plus 6y equals 3. What can I do with that? Nothing. Okay? So basically, we need there to be perfect opposites. You know why? I'll tell you why. Because when we add the two equations together, we want either the x's to be opposites and cancel each other out, or we could also either have the y's be perfect opposites of each other so that when you add the equations together, they will cancel each other out. So let's look at our system we have right here. Are the x's perfect opposites? Will they add up to 0? Heck no. Are the y's perfect opposites? Yes. Negative 2y and positive 2y are perfect opposites. When you add these up, it'll be 0. So since we have perfect opposites, we can go ahead and add these two equations together. So make sure there's a pair of opposites. Check. Add the two equations together. So 4x plus x is 5x. Negative 2y plus 2y is 0y. Don't even write it. Bring down the equal sign. 7 plus 3 is 10. Take a look at what this is compared to what we had over here a minute ago. 5x equals 10. Now we're getting somewhere because step 3, we can solve this for x. If you get rid of the y variable, you can focus on just solving for x. Solve for the remaining variable. All you have to do is divide both sides by 5. Boom. X equals 2. And just like the other method, once you know what x equals, you can plug it in for one of the equations, plug the 2 in for x, and solve for y. I'm going to pick this one. And yeah, because I think it's going to be easier. So x plus 2y equals 3. I now know that x is actually 2. So 2 plus 2y equals 3. And now you've done this a million times. Just do whatever you got to do to solve for y. 3 minus 2 is 1. I'm running out of room, so divide both sides by 2. Y equals 1/2, or 0.5 is fine because that's an exact decimal. And so my final answer is 2, 0.5, or 2, 1/2. And that's how the elimination method works, what I call the addition method. Now, if you subtract, well, I don't want to say that math pun. If you, like imagine I didn't give all that explanation. Imagine if I didn't take all that time to explain it. How quick was that method? Boom, there's opposites. Boom, add them together. Get this, get that, boom. How quick would that have been if you take away all the explaining I did? Now, of course, it helps if there's already opposites. Feel free to pause the video and try this example on your own. 5, 4, 3, 2, 1. Here I go. I look at this system and I see that there are already opposites. Not with the x's, but with the y's. The y's are already perfect opposites. Negative 1y, positive 1y, or just negative y and positive y. So I'm going to go ahead and pull the trigger on adding the equations together. 3x plus 2x is 5x. Man, deja vu. This cancels out. 7 plus negative 2 is 5. Again, 7 plus a negative 2 is 5. Now that'll get me an answer for x. So x equals 1. And now I just have to plug it in to one of the equations. I'm going to choose this one because I think it's going to be easier. So 2 times 1, so 2x, I now know that x equals 1, plus y equals negative 2, so that's 2. 2 times 1 is 2, duh. And now all I got to do is subtract 2 to both sides, and negative 2 minus 2 is supposed to be negative 4. And just like that, I have my final answer of 1, negative 4. This next example, feel free to try on your own in 5, 4, 3, 2, well, pause the video. I'm going to start in 5, 4, 3, 2, 1. Man, such easy problems so far. There's already opposites. This time it's with the x's at least. But yeah, that's fine. That's more than fine. Doesn't matter which variable goes away first. So yeah, the x's are perfect opposites, so I can go ahead and pull the trigger on adding the equations together. Negative 4x plus 4x is 0x, which is 0. Not even going to write it. Negative 9y plus 6y is negative 3y. Bring down the equal signs. And then negative 1 plus negative 2 is negative 3. By the way, it's not just about needing opposites. Everything has to be lined up as well, which it's almost like that goes without saying. That was like step 0. Everything's got to be lined up for you to even think about doing the addition method. But now, all I got to do now? I hate it when my board does that. But now I just have to divide both sides by negative 3. to solve for y. Negative 3 divided by negative 3 is positive 1. Now I'm going to plug 1 in for a y somewhere. I'm going to pick this guy because I think it'll be easier and nicer. So 4x plus 6 times 1 is y equals negative 2. 6 times 1 is 6. And now I find myself in a situation you've done a million times. Just got to get x by itself now. Divide both sides by 4. To finish solving for x, negative 8 divided by 4 is negative 2. And so my final answer goes x comma y. So negative 2 comma 1. Ooh. All right, the plot thickens. Question, what if the system given is not already perfectly set up? In other words, well, set up so that one of the variables will be eliminated when you add the equations together. In other words, what if you do not have opposites with the x's, and also you don't have opposites with the y's? Now you might be looking at this and going, well, we can do the substitution method. That wouldn't be so bad with this system. And you're right, but I want to do the addition method, the elimination method. So what do? Answer, you multiply to one or both equations by whatever it takes. Once again, this could probably be written a little better, like better choice of words. You multiply to one or both equations by whatever it takes to create opposites. So you're going to multiply whatever it takes, okay? You're going to multiply each equation or one of the equations by whatever is necessary in order to make the x's into opposites or the y's into opposites. For some reason I'm struggling choosing my words in the best manner. Okay, so hopefully you get what I'm saying here. We need to multiply this equation by something, or we need to multiply this equation by something. Like we need to change one of the equations or both of the equations, and the only way we're allowed to do that is by multiplying the equation by a number, or both equations by a number, by different numbers. And the whole idea is, if we don't have opposites to begin with, we need to make there be opposites. Okay? So now it's a matter of your choice, okay? Because again, your choice, and you're going to be multiplying the equation or the equations by whatever it takes. You know, it's like an open-ended type thing. So if you look at this equation, could I multiply this equation by something that would make the 2x into a negative 3x? Because if this was a negative 3x, we'd be in business. But what could we multiply to the 2x to make it a negative 3x? I don't think we can without going into like fractions and stuff, so no, but okay, what would be the opposite of negative 2y? What if that was a positive 2y? So can we turn this into a positive 2y? And I'm good with that. How are we going to multiply, like what are we going to multiply to here in order to make it a positive 2y? Well, all we need to do is multiply it by 2. But again, we need to multiply to the entire equation. So let me just change colors, okay? Just so this equation is going to become 4x plus 2y equals 10. I know we're focused mostly on making this the opposite of that, you know, like making this into a positive 2y, but we have to multiply the entire equation by 2 to keep this like basically the same equation and keep it all legal. Now, do I need to even change this equation? The answer is no. So this is going to remain 3x minus 2y equals negative 3. And am I good to go adding these equations together? Do I have opposites now? Heck yeah, you know, those are going to be gone. So 4x plus 3x is going to be 7x. Don't even need to write 0 or whatever. And then 10 plus negative 3 is positive 7. Now I can actually solve for x like I've been doing. X equals 1. And as always, now that I know x equals 1, I can plug it into one of the equations I've had in order to figure out y. Which one should I pick? Should I pick the original equation 1, my updated equation number 1, or equation number 2? Where do you want to plug 1 into? And I'm going to pick my original first equation, which I will rewrite. So, but now I know that x is actually equal to 1. Plug it in. 2 times 1 is 2. And all I got to do is subtract 2 from both sides to figure out that y equals 3. And so my final answer is 1, 3. Ooh. Picking it up a notch even more here, gang. So here we go. How am I going to solve this system? If I told you to do this by substitution, man, things could get ugly. So anyway, we're going to do elimination method, addition method. But check this out. Are the x's opposites? No, they are not, and not even close. Are the y's opposites of each other? No, they are not even close. So here in part A, I guess, for the sake of learning, you know, we're going to look to eliminate the x's, which means make the x's opposites. Why don't I just go ahead and rewrite the system, okay? 3x plus 7y equals 15. 5x plus 2y equals negative 4. Okay, we want to make 3x and 5x into opposites. What's the opposite of 5x? Man, so if only this was a negative 5x, can you multiply by something cleanly in order to make 3x into a negative 5x? Not without using fractions, which I don't want to do. I don't want to recommend you do. So here's what I am going to recommend we do. If we're in this kind of situation, 3x and 5x, we need to multiply both equations by something. what could I turn 3x into? What could I turn a 5x into? And so that they're the perfect opposites of each other. I know you got to be good with your times tables and numbers and stuff, but think about what can you make a 5x into? You can turn a 5x into 10x. You can turn a 5x into negative 10x. You can turn a 5x into 15x, negative 15x, 20. Like, think about multiplying to this equation to make 5x into something else, making 3x into something else. But I want them to end up being opposites. So, I can't really have all the answers for you. You have to, again, you got to kind of know your way around numbers. And so here's what I'm going to do, for example. There's not one correct way to do this. I'm going to multiply the first equation by negative 5 because my plan is to make this into a negative 15x, which means I'm going to have to multiply this equation by positive 3 to make this into a positive 15x. So here we go. Changing the equations. Let's change the color. So this equation remember, I have to multiply negative 5 through the entire equation, not just the 3x. So negative 15x, just like I planned, minus 35y equals, and then what's negative 5 times 15? Ooh, mental math. Negative 75, I do believe. And then the second equation is going to become, let's see, 3 times 5x is 15x. No surprise there. That's what I planned on happening. 3 times 2y is 6y. And then equals, and then 3 times negative 4 is negative 12. Wow. But at least my two new equations have opposites with the x's. So those are going to add up to 0, just like I planned. Negative 35y plus 6y is negative 29y. And then negative 75 plus negative 12 should be negative 87. Okay, well, but this is good. I have an equation that I can actually solve for y. So when I get y by itself, divide both sides by negative 29. I do believe that this will get me positive 3. Let me double check on my handy dandy calculator. Am I typing this in right? Yeah, positive 3. Whew! Well, it's all downhill from here, if not already. It was probably all downhill from here. But where am I going to plug this 3 back into? I got this option, this option, this well, actually, this option or this option. I'm going to pick this option. I think it might be one of the easier ones. So 5x, so remember I'm going with this one. 5x plus 2y, but now I know y is 3. So plug it in there. So 5x plus 6 equals negative 4. We've solved equations like this a million times. Just got to get x all by itself. Divide both sides by 5, and we get x equals negative 2, I do declare. And so my final answer is negative 2, comma 3. But check it out. We're going to solve the system again. No, we already know what the answer is supposed to be at the end of the day, but what if we decided to eliminate the y first? Because that was an option. It was an option. So let's see how that would play itself out. Just to show you that it doesn't matter which letter you choose to make opposites of each other. You know, sometimes there's a better option because of quickness and easiness, but In this problem, it was like a horse apiece. Like it was just as annoying to make the x's opposites as it's going to be to make the y's opposites. It's not like this 7y. Like if this 7y was actually like a 4y or a 6y, then that would actually have made the y's a bit easier. Anyway, let's cut to the chase. I want to make the y's opposites of each other. What's the opposite of 7y? Negative 7y. Can I turn this into a negative 7y with some clean multiplication? Nope. So I'm gonna have to change both equations. So what could I turn 7y into and 2y into with some clean multiplication so that they end up being opposites? I'll pause for a few seconds and let you think about it. Okay, now, I don't know if you came up with exactly what I'm about to do, because there is more than one way to do this. But I'm going to multiply this equation by negative 2, because I want that to end up being a negative 14y, which means I'm going to want to multiply this equation by positive 7, because I want this to be a negative 14y, and I want this to be a positive 14y. Let's change coolers. If it'll let me. Okay. Now remember, I got to multiply the negative 2 to the entire equation. So, like distributing. So negative 6x minus 14y, just like I planned, equals negative 30. And this equation will become 35x, you moron. 35x plus 14y. It's all going according to plan. Equals negative 28. Now I'm good to go. Now that I have opposites, I can add my equations together. Negative 6x plus 35x is 29x. Right? Those cancel out. Don't even bother writing 0y. And this will be negative 58. When I divide, and now I'm good to go solving for x. Easiest thing in the world. Divide both sides by 29, and I get negative 2. Was I supposed to get negative 2? Yep. I mean, that was normal. That's what was supposed to happen. We're solving the same equation or system twice in a row. And now what's the only thing left to do is plug this in to figure out y. I'm going to pick this equation. I think it might be easier. We'll see. But it doesn't matter. 5x. We now know that x is negative 2. Plug it in. Finish writing that equation. Plus 2y equals negative 4. That's negative 10. Now we find ourselves just solving for y like we've done 100,000 times. We get 2y equals 6. And shockingly, we get y equals 3, which we were totally supposed to get. So there's a lot of different ways to solve these things. But just to kind of recap here, sometimes you already have opposites, like it's nice. Isn't this nice when you already have opposites right out of the gate? That's when you really want to pick the elimination method. Talk about being perfectly set up for elimination method. Now, sometimes you are going to pick a certain letter. Like when I look at this one, I go, ooh, I'm not going to pick the x's to make opposites, even though I could. I'm going to pick the y's because that way I only have to multiply something to one of the equations like I did in this problem, you know? But sometimes you're left with like no choice. You have to multiply both equations by something in order to make either the x's opposites or the y's opposites. Oh my gosh. Should we include this on the video? Would it be worth it? Yeah, let's do it. Why not? Even though my throat's starting to hurt a little bit. Question that has no doubt been eating at you since we started solving systems algebraically. What kind of answer do we get when there's actually no solution or infinitely many solutions? You know, well, actually, these are the final answers, but, you know, what do you see in these methods when there actually isn't an answer? You know, like, if there's an answer, you're going to end up with x equals some number, which leads to you getting y equals some number. But if there's no solution, what are you going to get? X equals, like, what's going to happen? Because there are systems that have no answer at all, and there are systems that have infinitely many answers. So what happens when you're working your way through these methods? Like, what happens? Let's see. So activity, okay? Create a system that you know represents two lines that are parallel. Thus, so what happens? When two lines end up being parallel, that system will have how many solutions? No solutions, okay? So here we go. Let's do this way. Y equals 3x plus 2, okay? And for the other line to be parallel, it's got to have the same slope. Doesn't matter what the rest of it is. Minus, I don't know, who gives a crap, minus 5. As long as these slopes match, the lines are going to be parallel. Well, you know, since they're written the way they are, you know, they're both set equal to y, let's do the substitution method. Because it's going to be super easy here. They're both equal to y, which means we can just set them equal to each other. It's like the easiest case of substitution when they're both equal to y, and you can just set them equal to each other. So 3x plus 2 equals 3x minus 5. So here we go. Substitution method engaged. We already did it. So that was the substitution part. Now we can solve for x. Let's get the x's together on one side and wait. Ah, that is gone as what the, it looks like my x variable is completely canceling out, and what I'm left with is just 2 equals negative 5. Which, since the variable totally dropped out and disappeared, what I'm left with is either true or it's false. So does 2 actually equal negative 5? No, false. Dirty lie. And so if it's false, what that means is, of course, what we should have been expecting, or we should know what the final conclusion is already, that there is no solution whatsoever. So if the system is destined to have no solution whatsoever, this is what's going to happen. The variable is going to totally cancel out, and what you're going to be left with is a completely false statement. So you're not going to end up with x equals 7, x equals -1. You're going to end up with something completely false, and then you can go ahead and stop right there and conclude that there is no solution if what you have is completely false. When there is create a system that you know represents two lines that are actually the same line, so you have infinite solutions. By the way, this same result would happen if we somehow used elimination method. Doesn't matter what method, substitution, elimination, this is what happens that lets you know that there's actually no solution, okay? Because I think what I'm going to do in here is, again, the substitution method, but it doesn't matter, okay? Like whatever method you do, the result is going to be the same. So let's do like 2, like y equals 1. Let's just make it clean, you know. -2x minus 6. And if the other equation is going to be the exact same line, it's going to have the exact same equation. So once again, I'm going to pick the substitution method, which means it's already good to go. We can just set these two equations equal to each other. And so when we work to get the variable only on one side, it happened again. The variable totally cancels out, but what you're left with, in this situation anyway, is -6 equals -6, which is completely true. And when that happens, you can go ahead and conclude that there is infinite solutions to this system. So once again, you don't end up with x equals some number. The whole thing just sort of breaks down, and from there it just depends on what you have is true or false. Just like before, I mean, this is not a new concept to you. We've done equations where you end up with like a true statement or a false statement, and so this is not a new concept to you, actually. It's just you probably didn't know that this could happen with the substitution method or the elimination method when solving systems. And so, man, what a section. What a video. But we're done. So I hope that all made some sense. You can always ask me one-on-one in class, or just watch the video or parts of the video over and over and over and over again. So that's it.